Hello, Stat 200, and welcome to Lesson 6. This is the second of 2 lessons on hypothesis testing. This week, you'll finish reading Chapter 4 in the Lock 5 textbook. Last week, you learned how to conduct a hypothesis test using randomization procedures in StatKey. This week, we're going to delve a bit deeper into hypothesis testing and look into some conceptual issues. These are the key topics that we're going to cover this week. In this video, I'll give you a brief overview of each topic. Then, in the online notes and in your textbook, you'll read a bit more. Let's start by looking at errors. When we're conducting a hypothesis test, there are 2 possible decisions. We can reject the null hypothesis and conclude in favor of the alternative hypothesis, or we can fail to reject the null hypothesis. When conducting a hypothesis test in real life, we don't usually know the population parameters. So in most cases, we don't know if our decision is correct or incorrect. In reality, the null hypothesis could be true or it could be false. When we reject the null hypothesis, either the null hypothesis is really false and we made a correct decision, or the null hypothesis is true, in which case we made an error. This is known as a type 1 error. When we fail to reject the null hypothesis, if the null hypothesis is really true, then we've made a correct decision. If the null hypothesis is really false, and there really is a difference in the population, then we've committed a type 2 error. A type 1 error is sometimes known as an alpha error, and a type 2 error is sometimes known as a beta error. This brings us to the idea of significance levels. The significance level, also known as the alpha level, is the highest tolerable probability of committing a type 1 error. In other words, it's the largest p-value for which we would feel comfortable rejecting the null hypothesis. The standard alpha level is 0.05. Unless otherwise specified in this course, always assume that alpha is 0.05. There are some situations, though, where you might want to use a lower or a higher alpha level. For example, in a pilot study. A pilot study is a smaller study that's performed typically before a larger study, usually with a smaller sample size. The purpose of a pilot study is usually just to get information about the variables that you're interested in studying. So for pilot studies, we often use a higher alpha level because the purpose is just to gain information about the data that we're really going to look at in a later, larger study. Studies in which making a type 1 error would be more dangerous than making a type 2 error may use a smaller alpha level. For example, a lot of medical research uses an alpha level of 0.01 or even 0.001. This makes it less likely that we would commit a type 1 error. The next topic you'll see this week is issues with multiple testing. If we would conduct 100 hypothesis tests at a 0.05 alpha level, if the null hypotheses were true, we would expect to have statistically significant results for approximately 5 studies due to type 1 errors. Later in the course, we'll learn about some statistical procedures that can be used in place of multiple testing. So for example, if we wanted to compare the means of 3 groups, instead of conducting multiple pairwise tests of differences, we could conduct a one-way ANOVA. If we wanted to compare the proportions in more than 2 groups, instead of conducting multiple pairwise differences in proportions tests, we could conduct a chi-square test of independence. We'll see both of those tests towards the end of this semester. A problem related to multiple testing is publication bias. So studies with statistically significant results are more likely to get published than studies without statistically significant results. This is a problem because if we're doing a review of literature, we only have access to the results that have been published. So we only have access to the 5 studies that have statistically significant results, not the 95 studies that did not have statistically significant results. so the research that we're able to review may be biased. The next topic that you'll read about this week is practical significance, also known as effect size. This is the magnitude of the observed difference. So statistical significance answers the question, is there a difference in the population? To examine statistical significance, we construct a sampling distribution and identify the p-value. Practical significance, on the other hand, answers the question, how large of a difference is there? This is where we could look at the sample statistics and compare them. For example, in your notes, you'll learn about Cohen's d this week. If we're comparing the means of two groups, we can compute Cohen's d as a measure of effect size. This is the difference between the two sample means in standard deviation units. So while statistical significance is looking at a p-value to determine whether or not there's evidence of a difference in the population, practical significance is just looking at the observed sample statistics, comparing them to the values in the null hypothesis, and asking, is there a meaningful difference here? The second to last topic that you'll read about this week is power. Power is the probability of rejecting a false null hypothesis. If we go back to the table that we saw earlier, it's essentially a conditional probability. So, given that the null hypothesis is false, the probability that we would reject it. A type 2 error is known as a beta error, so sometimes you'll see power written as 1 minus beta. And finally, the last topic that you're going to read about this week, this is covered in section 4.5 of the Lock 5 textbook, is confidence intervals and hypothesis testing. You're going to compare and contrast these two inferential procedures this week. So both confidence intervals and hypothesis testing are inferential procedures. They take data from a sample to make an inference about the population. They differ in terms of how the sampling distribution is approximated. For confidence intervals, we don't have an estimate of the population value, so we use bootstrapping methods. The bootstrap distribution is centered on the observed sample statistic. For hypothesis testing, we do have a hypothesized population parameter. So the randomization distribution is going to be centered on the value that's in our null hypothesis. A 95% confidence interval is comparable to a two-tailed hypothesis test at the 0.05 alpha level. You'll see some examples of this in your textbook this week. So if we were to construct a 95% confidence interval, that would give us a range of plausible values of the population parameter. Any of the values within that 95% confidence interval are plausible or reasonable values of the population parameter. If we were to conduct a hypothesis test using any of the values within that interval, we would have to fail to reject the null hypothesis. Any values not contained within that 95% confidence interval are not plausible values of the population parameter. If we were to conduct a two-tailed hypothesis test at the 0.05 alpha level for any of those values outside of the confidence interval, then we would reject the null hypothesis. You'll see a few examples of this week. This concludes the Lesson 6 overview. As always, if you have any questions as you're working through this week, please post them on the Lesson 6 discussion board in Canvas.